Hi, my name is Jim, and the analysis method we're going to talk about right now is called superposition, and the problems we're going to be using are the same that we used for mesh and nodal. And in superposition, what's very important is to replace the respective source by its internal impedance. Now, for a voltage source, that's going to be 0 ohms, and for a current source, that's going to be infinite ohms, open circuit. So you absolutely have to know that when you're using superposition to solve problems. So basically the way it works is we let one source be active at a time and then find a partial solution, then let the other source be active and find another partial solution, and then add those partial solutions together to get the final solution. So here we have our problem, like I said, as we did before. And what I'm going to do first is I'm going to let V1 be active, and I'm going to remove V2 from the circuit and replace it by its internal impedance. And since it's a voltage source, its internal impedance is 0 ohms, and I've indicated that by a dot going around the source. So if we look into this, is what we see is we have 8K in parallel with 3K. In parallel because the top of the 8K connects to the side of the 3K, and then the right side of the 3K connects through the short circuit, if you will, of the voltage source to the bottom of the 8K. So those resistors are in fact in parallel, and that gives us a total value of 2.182K. So what we're going to do is find our first partial solution. I'm going to call that VA1, and that's simply going to be equal to a voltage divider, with the numerator being 2.182K, and in the denominator will be the sum total, and what we get after we do that voltage division is 11.48 volts. So what we can say is that 11.48 volts is produced by this 22 volt source. Next, what I'm going to do is let V2 be active, and I'll take V1 out of the circuit, and by doing that I have to replace it by its internal impedance, which is a short circuit, so I'll just kind of draw a couple dotted lines there to indicate that. And what I want to do here now is find VA2, which would be the partial solution provided by the 12 volt supply. So looking into this, is what I see is I have 8K in parallel with 2K because of the short circuit here, and we take those in parallel, is what we get is 1.6K. So what we end up with for VA2 would be, using voltage divider again, it equals 4.173 volts. So we have two partial solutions, and then finally the voltage at node A, which allows us to completely decompose the network and find all physical currents, is going to be equal to the sum of the partial responses, and that would be 11.48 plus 4.173, which yields 15.65 volts, which is the same answer as we had before using one of the other methods. So the nice thing about this, I suppose, is we don't get into a system of linear equations with this, and we're just using, basically in this example, series parallel analysis techniques. So let's take another look, only this time we'll have a current source involved here. So I'm going to start by letting V1 be active, and there's no magic to that. You can let whatever source you want to be active first. And we're going to find a partial response again, and this time, instead of replacing the source with a short circuit, since it's a current source, I have to replace it with an open circuit, which basically says that R internal is equal to an infinite resistance, meaning realistically that no matter what the voltage is across the source, the current is going to remain a constant 14 milliamperes. So what that looks like is I have the 3K resistor here connected to nothing. It's not in the circuit, hence there's nothing in parallel with the 8K. So that's pretty easy. We'll just find the partial response at VA here, calling that VA1, is going to be equal to our 20 volts times, in the numerator, 8K, and in the denominator the sum of the total resistance, and that equals 16 volts. So that's our first partial. Now I'm going to let I1 be active. That's our current source here. And then what I would have to do is replace this by its equivalent internal resistance, which is a short circuit. So what that'll do is put 2K in parallel with 8K again, which will give us 1.6K, and then that's going to be connected to our current source of 14 milliamperes, and then the current is going to flow in this direction up through the resistor, which means that the top of the resistor here for V1, I'll call it 2, VA 2, there we go, all fixed, is going to be negative with respect to ground. So working that out is what I get is 14 volts times 1.6K, and that yields a negative 22.4 volts. One last thing to do is add up the partial responses here to get the total response. So V at node A is equal to VA sub 1 and VA sub 2, 16 volts plus a negative 22.4 volts. And do note that I could simply put a subtraction sign in here, but I mean being explicit just to make sure that I don't make any mistakes, and I urge you to do the same thing. And that gives us a node voltage here of VA of negative 6.4 volts, and that's the same as we got with the other analysis techniques. So that'll conclude for superposition, and thank you for watching.